All right, real quick, we're gonna do a quick note here. Once we're done today, we are finished, done, complete. I just want to talk about, yesterday we did the graphs of limits from the right and left side. Today, we're going to look at how do you do it with functions, the actual formula. Now, I did an easy one yesterday. I'm going to kind of make some more challenging ones. So my goal is to do about 3 or 4 quick examples, like in order, and then we'll see kind of where we're sitting, okay? So first one, here's the first one I'd like you to write down. F of x, let's go with something kind of easy for right now. X squared minus 3x plus 2. And the idea is that I want the limit as x approaches 1 from the left of f of x. So this is something that you need to get used to seeing in the book. They don't give me a graph to go with this one. They want you to figure out what is it going to do when it's approaching 1 from the left. Now here's the thing. When I look at this problem, the things you should think about. Now obviously other than what it looks like, okay, is there going to be a problem if I just, instead of like looking at the left side, is there going to be a problem if I plug a 1 in there? Will it put like a 0 on the bottom of a fraction? Or will it make a radical like negative? Well, in my case, is there any problem with me just plugging 1 in? No. Just plug it in then. That's literally how you can do a limit. If you can plug it in and it doesn't cause a major issue, just plug that into this function and figure out what you get. So in my case, I'm just going to plug in 1. I'm not going to worry about the left or right side because it shouldn't have any problem. So 1 squared minus 3, plug in a 1 because it's not going to have any fractions. It doesn't have any radicals. So I'm going to get 1 minus 3 plus 2, and yeah, I already heard it. We're getting a limit of 0. It's approaching 0. That's your answer, right? Even if you approach from the left or right side, this thing is actually going to one single digit. It's going to one number. So when you actually look at the graph, and when you're looking at the graph, it's probably doing something like this, okay? Or it's at least close to it, okay? Questions on the concept of what we're doing? All right, so that's the idea of what a limit is. Now, obviously, you're thinking about this and you're going, Ward, how would that be any more difficult? Like, I don't understand. Well, when we start looking at it, here's the problem we could have.
Hey, time out. I ain't sure.
Better go quick.
Lorna, return her calculator.
Thanks.
I know. Well, guess what?
So, this problem, we have an issue, right? We do have an issue on this problem. I can't plug in a negative 2, okay? Because if I plug in a negative 2, it'll make 0 on the bottom. You can't divide by 0. So right now, the function looks like it's undefined at that moment, or the limit does not exist. But remember, you're always allowed to simplify things. So if you are able to, simplify the fraction down and see where that item is going. Now, when I actually simplify this is called a rational expression. You do need to know how to factor. So that is the difference of squares on the top, the bottom. I literally can't do anything with the bottom. Now, as I get to this point, I can cancel out the x plus 2's. Now, what those are called removable discontinuities. There is literally a x number that I was not allowed to have, but it removed itself. So if you actually looked at a graph of this thing, and you're looking, and you're approaching negative 2, there probably is an open circle there. Even though it removed itself, you probably won't see it on an actual graph because it will be so small. It's 1 pixel length, you know, like what screen you're looking at. It's 1 pixel in length and width. And the idea is you may not see the gap, but there is an actual hole, but it did remove itself. That way you can actually evaluate a limit for it. So as I approach from the left and right, and I plug in a negative 2 into this problem now, right? That's plugging negative 2 because this is the only thing that's left, right? What answer am I getting?
Negative 4.
Negative 4. And so that is actually the limit. It actually ended up being a number, even though it was undefined originally at that spot. Because what's happening, now I don't have my graph run right, but at some point, at negative 4, it was actually, it had an open circle there, but it actually had as a number now. Does that make sense? Like the limit actually exists. Question?
Do you
What?
Think stuff. Is there right there by Drew?
Is that so? Is this right here?
That's mine.
Is that it?
Drew, you can't
Drew,
write
look
yourself.
at it. Check the name on it.
Dude, there's a notebook
Look
right
at
there.
Same.
There's a name on the
Same.
computer.
Jane Hackles
Okay.
thing with it.
Think
There you go.
please slide it this way.
And
Thank you.
Judas
Sorry,
Christ.
sorry to make you work. Thank you. Thank you.
Yonkers.
she burned you so hard, Drew.
Thank
I bet it's.
She
I
said
bet
something about notes to me.
Yes.
I bet he
She
needs
told you to
some
take
eyes
notes,
for that.
Drew. I bet it hurts a little bit. So.
Probably
All right.
like
So-
speak at a normal
all right.
pace so I can actually take the criticism.
So. Okay. Now, let's keep going here. Next thing. We're going to be talking about if this thing were to approach infinity or negative infinity. So the example that the book has for like functions. Let's say I had something like this. It's 3x minus 1, and on the bottom I had 4x squared plus 5x minus 2. And this is my function, right? And I want to know what happens when the limit as x approaches positive infinity for my x.
Oh, that was nice.
So for my f of x, I should say. Okay? As I approach positive infinity. All right, now here's the thing. When you look at that graph, it actually has a horizontal asymptote, right? If I was just thinking about what this thing looks like, it actually has a horizontal asymptote at 1/4, right? Because they have the same powers on my actual like functions. They're both x squares. It's a rational problem. So, since this has a horizontal asymptote at 1/4, this is the number 1. This is literally the number 1/4. That means the outside tails, like the end behavior of this graph, the end behavior of the graph, whatever it is, it's actually approaching that number. Okay? Because that's the numbers that we're approaching. So when we go to positive infinity on the x-axis, that's the reason why we have an actual horizontal. It's because it's telling you what your limit's going to hit. Your limit, as you approach positive infinity, when I plug in bigger and bigger numbers here, here, and here, these things basically all go away because they're making the same number. They're making a really large number, like infinity over infinity, which literally like divides out. And your answer is literally going to end up being a 4th. It's going to flatten right at those spots because I don't care that the top and bottom had different numbers, like 3s and 5s and 1s and 2s. They will literally go to infinity and they'll cancel each other out because I could have factored out a 1 and I could have factored out a 2, and these things would eventually cancel out because they're almost the exact same number anyway. It's the weirdest thing in the world when you start thinking about that when you go up to such bigger numbers, they're so big anyways, they're literally the same number in theory. So that's why they would cancel out and you're left with the leading coefficients. This is one of the hardest concepts to like wrap your head around because most people try to argue that these are going to approach infinity at different paces. Right? This one might go faster than the other one because it has a 5. But they're still going to such a big number that when you divide them out from each other, it almost makes the number 1. And so it's 1 times a 4th out front. It's this concept where you have to like think about in terms of like infinite numbers. It's one of the hardest concepts to understand. Now the last type of problem I want to talk about is the idea of like what happens when you approach negative infinity, but I want to do it for this. As you approach negative infinity on 1 over x. So I'm going to start plugging in bigger numbers, right, into this bottom. I'm just going to give you some examples, like, because I'm going towards negative infinity, so like negative 1,000. The next number I'll try is maybe negative 100 million. What type of number am I actually coming up with now? Like what is this type of number? Say?
Fraction.
It's a fraction, it's a rational number, right? But as I pick bigger and bigger numbers as I go towards negative infinity, really big negative numbers, right? What is the fraction actually turning into?
0.
0. It's literally, you said it right, the fraction is literally getting smaller and smaller and smaller in terms of digit value. I'm actually getting closer and closer to 0. Because what it's doing is it's doing something like this. So it's literally approaching the number 0 as I get closer to the x-axis. So it's doing something like that, where as I go out here, it's hovering next to 0. And that would be the limit in that case. It's a weird situation, like when you have to think about in terms of infinity, where that thing is heading, like what is it flattening out against? It's one of those concepts you just don't think about. Now, the other reason is when you look at it, when you look at horizontal asymptotes, is the top bigger than the bottom in terms of power? Is the top bigger than the bottom in terms of like degree? No, this degree on the bottom is bigger, right? It's x to the first, this one's x to the 0. What we talked about when we graph, anytime the bottom is bigger, you have a horizontal at 0. So that makes sense now. When you talk about a limit, as you go further and further out, it's going to hover against that asymptote as it gets closer and closer to 0. It's one of those things like starting to see the concepts of like these little rules that we have for functions. Like what happens when it goes to infinity, you have to think, is there a horizontal or is it just going up forever? So like, it would, what they would say, like if it just went up forever, let's say I was doing a problem like this, where it was just x as the limit as x approaches positive infinity. The idea is that I'm going to be plugging in bigger numbers here, so my answer is going to approach, or it's going to, what do they say? It's going to, there's a term for it. It's going to head towards, or what is the term? They have a term for it. It's not approach. They have a fancier word for it.
Go.
Let's see. What's the word I'm thinking of? It's going to.
All right, please don't work on
I said sorry.
it. No, sorry.
Here.
Approach.
No, it's not
Limit.
not approach. There's a certain term for
Get
it.
closer to it.
Nah. Diverge. There's the word. It's going to diverge towards positive infinity. I know it's approach. It means to diverge. It's heading towards that direction. And the idea is that when you're heading that big, I know that that number, like, that's literally not even a number. I understand that. If you said that this limit doesn't exist, I would understand what you're saying, because that would be valid. Like, there's no limit to this problem. It literally goes forever. You could also say that it diverges towards this direction. It's heading up. That's just a different way of saying the same thing. Now, what we were talking about yesterday when we were looking at pictures was this concept that when you look at pictures, it's much more easy to figure out, limits. So when you look at a limit from the left and right side, you're hoping that they're going towards the same number, right? As I approach 1 from the right side and the left side, this is the answer I want to be going towards, right? So the limit as this function gets closer and closer to 1 from the left and right side, my answer would be 1. Now, here's the weird part. This is what we discussed yesterday. What is the actual function value at 1 though? Well, the function value doesn't even have a number. Maybe there's a solid dot somewhere else on this graph where there's an actual number there, where that number is 4.5 or 5, whatever you want to call it. The actual value might be a different digit, like the function value when I plug in 1 into the formula, but the limit is where the curves are going. What numbers is the graph approaching from both sides? Does that make sense how they could be different numbers?
No.
So,
I'm just lost out of what you're trying to say.
okay.
Sam's lost.
Okay, how do I explain it?
If Sam's lost, we're all
I've
lost.
been working on it.
Okay, a limit. So when I hear the word limit, you're thinking, okay, I'm going to look at the picture, and I'm going to go from both sides, and I'm approaching this x number, right? So do you see the x number right here?
Yeah.
You go to the graph and figure out where the curves are going to that. So I'm watching. So if you're following, I'm getting closer and closer to 1, and my fingers are going to stay on the curve. And where will my fingers end up at when I get to that number?
Uno. 1.
1. That's a limit, right? It's like, where is that graph going? That's a limit.
So why is the dot not on the graph?
So the dot doesn't need to be on the graph. So it's an open circle there. Maybe there was some horizontal number that I couldn't plug in there. Maybe like it was being divided by x plus 1. So like we don't know what the function is. It could have been any like rational thing. So maybe it had something like the function f of x could have been something on the top, but on the bottom maybe it had this. Or, sorry, that. So I couldn't plug a 1 into it. So there's an open circle there. But somehow, like, they just evaluated, maybe it was a piecewise function, and they told me later on that the function value at 1 was like some other number. The function could have a different answer, like the function itself for a problem could have a different answer than where the graph is actually pointing. Because maybe it's a piecewise function, there's like different spots on a graph where the graphs are going. It doesn't have to be just one function itself. So, I want you to notice the difference between how you evaluate a function when you plug in a number versus what a limit means. Limit means follow the curves on the graph. Because they could be different numbers completely.
You have an example where that happens?
You should put it down.
Yeah. Okay, I'm going to give you an example, okay?
Good try, but I needed it.
Somebody take my notes.
So would this only happen on a piecewise function? Like it cannot happen on a continuous graph?
This graph would be a piecewise, because they have different things going on.
I'm gonna be the arch. Sorry, I didn't see you.
There. That's the idea. So from the left and right side of 1, it's doing some graph, this thing, but at 1, that's the answer at 1. Because you could have literally, like on a graph, you could have like multiple different graphs going on, like for your data for your business, and you're trying to figure out where's the data pointing towards. Like, why do you suddenly have like way too much money in the bank when your graphs are saying that you should have like $1,000? And you're trying to figure out why the data is skewed. I mean, that's literally what it would be used for. Because maybe somebody hasn't deposited a check yet or withdrawn money yet. It's like the bank's statement is not matching your books, what the money should be. That's literally the case when you get audited by the federal government for tax. It's like when the numbers aren't matching up. Like you're spending too much money, you're buying too expensive of cars for what your salary is per year. Something's not matching. So, and they keep track of that stuff because they're just plotting numbers every year. Limits, it's one of those concepts, it's just tough to talk about because there's so many like weird things you have to discuss. Okay, all right, that's all I want to do today. I just want to intro the idea of like how you evaluate functions. We're going to do more this Monday so that I'll come up with a ton of different examples for it. I'll pull a bunch. We're going to probably get an assignment on Monday. It'll be something short, won't be big, it's going to be kind of short. It's going to be based on both graphs and evaluating things. I'll have different styles of problems. But there you go. If I called your name earlier, you owe me something. I'll probably send you an email this weekend stating like you need to turn in homework by Monday because there is literally a 10-day due date on